So welcome back to the seminar, everybody. So next we're diving into the world of virtual reality. The next 3 hours will be sort of different sides of VR. And the first presenter will be the CEO and co-founder of Delicode. So please welcome Julius Tuomisto.
Thank you. Hi, everybody. So I'm Julius Tuomisto from a company called Delicode. And today's talk is basically about making use of volumetric content for immersive VR experiences. And volumetric capture in this context, in the context of my presentation, is basically about character and actor capture using off-the-shelf hardware. And you could call this outside in rather than inside-out volumetric capture, which is kind of the thing that the bigger companies at the moment are very focused on, apart from Microsoft. And I'm going to try to tell you about volumetric capture. How does it differ from two-dimensional video, motion capture and animation, especially for the purposes of VR. And then I'm going to try to kind of speculate where this type of content fits in the AR, VR ecosystem in terms of content creation. The table of the proceedings is basically it. I'm going to just introduce a little bit more about myself and about my company. I'm going to do some quick preview of the state of the art presentation about basically some of the companies that are developing things on the field. Then I'm going to showcase 2 projects that we've done at my company, Delicode, in the past 6 months or so. And then I'm going to go through the technical workflow of those projects. And finally, I'm going to talk a little bit about the creative process and then again go back to the market fit. And then hopefully get a few questions from your end. Just about me quickly, I'm I guess ancient already in terms of assembly. I used to play a lot of Commodore 64 games and in the 90s, I used to use something called PBSs. I've been on the stage here a few times. The first time was maybe 6-7 years ago. I was talking about RenderFarm.fi at the time, which was a Blender render farming solution that we built at those times. I'm also a proud father now, so here's the version 2. Then about my company, we are now kind of finally found a nice slogan for us. We are a creative computer vision and machine learning agency. So that sounds very cool. Actually, we're just 3 guys from Helsinki. But we're basically co-founders, and we share kind of a long background in Blender and the related community. Currently, we're focused on finally focused on 2 tracks. We're doing the boring stuff, which makes a big part of our business, is actually people flow and analytics. So we compute how many people are in a certain space. But then we're also, because of our long interest in the arts, field of arts, background in it, then we've also been dabbling for many years with different capture methods. And this is what this talk is about. So just going into the state of the art, I'm actually going to show a few videos now. The first 2 videos are from Microsoft, which I feel is very much the place to be at the moment if you're dabbling with this type of content. And then I'm going to show another company called ARTtech, some videos, short videos from them. And then I'll go into our videos. So Microsoft Research has a long time focus on content creation, and it shows on their advanced workflows and their capability to produce even streamable content, volumetric content.
In this video, we present our system to create high-quality, free viewpoint video that can be compressed to bandwidth suitable for consumer applications. This example is a traditional Maori Haka performance. We start by capturing performances with 106 synchronized RGB and infrared cameras on a calibrated green screen stage. We subtract the background to compute silhouettes, then schedule the data for processing. The first step generates a 3D point cloud starting with stereo depth maps from RGB and IR pairs. Points from these depth maps are merged and refined locally. Then the cloud is refined globally using a multi-view stereo algorithm. This result has over 2.7 million points with normals per frame. We're viewing tens of thousands of points in this scene. The next stage creates a watertight mesh per frame. We modify screen Poisson surface reconstruction to produce meshes constrained by the silhouettes. These meshes typically have topological artifacts and spurious components. To clean them up, we apply topological denoising and island removal. This result has over 1 million triangles per frame. Next, we determine which areas contain perceptually important details such as hands or faces. We preserve the quality of geometry and texture in these areas when we decimate the mesh to its target density. This example is reduced to 20,000 triangles per frame. We then establish temporal coherence by choosing mesh keyframes and deforming them to fit ranges of the performance. This coherence is critical for compressing mesh motion and textures.
I'm going to just stop it there. So this is a kind of a unique thing that Microsoft is capable of doing. At least I haven't seen anybody else do this. And it's a kind of a key component in, and just as the video said, it's a key component in being able to stream this kind of data across networks. The amount of data is so high that you would need to do something like this in order to produce any kind of real-time streaming. I'm going to just move on to the next video, which will actually showcase now, because I'm not from Microsoft and because I haven't really been able to talk to the guys, I don't have an NDA or anything, so we've just figured out most of the things from the videos by ourselves. But then moving on to the next one, it's actually about HoloLens and then using a kind of a similar, probably not as high quality mesh, but doing something similar in a context of real-time performance.
Hi, today we're going to show you an exciting new technology that could fundamentally change the way that people will communicate in the future. Imagine being able to virtually teleport from one space to another in real time. Hey Sergio, how does it feel like to be holoported?
It feels great to be holoported.
So if Sergio is to wear his HoloLens device, and I'm going to wear mine, we can see each other in full 3D in real time. We can interact and communicate as if we're co-present. Sergio, can you walk around my space? Can you walk behind this chair? So we're doing everything to give the impression that Sergio and I are present in the same space. Sergio, let's just do a high five. That's great. Thank you, Sergio.
So that's basically what they're doing is exactly what was presented in the previous video, which was real-time meshing and then distributing that data over the network, which is something that we cannot do at the moment. Actually, I'm going to take a step back now, and I'm going to present a company called ARTtech, originally founded in New Zealand, and then now with offices in LA and SF. And ARTtech is a company that focuses on the kind of the previous step of this type of production. So it's the actual creation of the point cloud, which is the prerequisite of creating the mesh.
Pronto para treinar?
Now that's a heavy marketing video. Actually, they don't even show what the resulting point cloud looks like, but you can kind of get a glimpse of it in this second video that I show. This is an app that you can get for the Google Tango. It's called Holo.
Let's take a selfie.
The basic context of the app is that they basically digitized different actors and different animals. You could even see a tiger there, and then you can place them in an AR context. You can place them in the world. The results are quite convincing when viewed from far. As you move closer to the actual objects, you kind of start to see the point cloud and so forth. Then I'm going to actually go to the examples that we've created, which showcase a kind of a rudimentary approach to it, but the results are actually not that far away. I mean, you would expect that. So from reading about ATI, for example, they have a rig of 41 cameras. They create the point cloud out of this. Using these cameras, and then as you saw, Microsoft had a rig of about 120 cameras. So I mean, going down to 3 cameras, you would expect that you would get a kind of a big downgrade, but surprisingly, you can get pretty decent results even with the Kinect. So first, I'm going to show you the first project was called Smoke, and we filmed this one in March at Wiley. And it was a part of the Wiley beta program that Wiley runs at the moment. So this one is a music video for a Finnish band called Phantom. We haven't really released either of these, but you can actually, after the presentation, if you would like to come and see them, you can come to the stands, the Finnish VR Association stands, and take a look. Then I'm going to just skip that to make the presentation a little quicker, move forward. Then the second one, unfortunately this one doesn't have any sound yet. It was filmed in June at the Järvenpää Circus School here in the capital region, in the city of Espoo. And this production was supported by the Finnish Cultural Foundation. This one hasn't been released either, but we're working to do so for the autumn. This one differs from the visual point of view quite a lot, but unfortunately it doesn't have sound yet, so if you come to the stand and experience it, you will have to do so without the sound. But here you can actually very much make out already what this kind of type of capture, even with the kind of rudimentary rig that we have built, can look like. And this was filmed, as you can probably make out, this was filmed through the headset actually directly. And the actual show is it's an interesting concept that we came up with, I think 4 years ago. I started talking to this ARTtech, which is a group of local circus performers here in Finland, kind of prominent acrobats. And we decided to to make an outdoor performance for which we used actually the Kinect for visuals. We have a background in this. I won't go into that so much now. But then we kind of took the idea forward and decided that we might as well try to make a VR presentation of the performance. Okay, so I'm actually going to go to the technical workflow now, which is probably maybe the most interesting part for people here. So just to kind of point out again, we have been focusing on a very off-the-shelf solution to the whole problem. So we don't have those 41-point Craig cameras, you know, a single point Craig camera and then accompanying hardware would probably run you for 2,500–3,000 euros. So 41 of those or 120 of those, that's a lot of money. We're just using a couple of Kinects that you can actually buy from basically any store and run them to computers that are powerful enough. Then the kind of the plus sides of this type of approach is that we do have real-time depth map generation and the capability to kind of stream it to the computer. The depth map and RGB are actually relatively good quality from the Kinect for Xbox One. The sensors have quite a wide angle lens, so they actually give you pretty decent coverage. And of course they're extremely cheap and available almost anywhere. Now the minus parts of running this type of hardware compared to the solutions that ATI and Microsoft are doing, for example, the first thing that you will immediately notice is that there is no frame synchronization between the devices. So because we don't have the capability to actually put a clock into the device, this means that we don't have phase lock. So each of these cameras are totally independent. They don't really know about each other. And because of lack of phase, if I were to, for example, if you're shooting something in 30 frames per second, like we are with the Kinect, if I'm moving my hand very fast, like people normally do, you know, if you move your hand very fast, the other camera from this side might capture my hand while it's in this position, while the other one will capture it slightly later, just a few milliseconds later, and there's already a kind of a big gap between this, from the information that I have on this side and then the information on the other side. So this is a problem. Now there's another kind of a DOE thingy, which is totally unnecessary, but for whatever reason, the Kinect has an automatic exposure set to it, and in low light conditions, the Kinect firmware drops the RGB camera to 15 frames per second. You know, if you're trying to capture a texture to go with your depth map, then that's not kind of acceptable. Now also there's a slight, it's not fully synced to the RGB, and the depth map are not fully synced. So there's another little, like there can be another little difference between the depth map of your hand and then the actual RGB image. So it might be, you know, it might be small or it might be big depending on the frame. And of course, there's you can run into interference if you're using multiple cameras. A typical capture setup, like the one that was used for the proceedings that you saw, would be like this. And the capture area is basically we call the capture area the amount of volume that all of the cameras can see from each angle. So depending on how far away your cameras have been set up, the bigger the capture zone. If they're very far away, you have a bigger capture zone, but obviously you're losing a lot of resolution. So you want to kind of think of your scene and run the type of capture area that is best for what you're trying to do. Now, what we've also learned is a kind of a nice trick is to always think that one of those cameras is basically the starting position for the viewer. So you place a single camera, for example, and if you can, it's very good to place it at a very where a normal person would be looking at, so at a height of maybe 160 centimeters. And then the kind of the background cameras are kind of supporting cameras that give you more of the depth map and give you a more sense of depth into the actual final frame. Of course, later while the user is using your content, they are not in this type of content. They are not. They don't have to stay in position, so they're totally free to move about if you so decide in your scene. But it would be advisable to have an initial perspective in mind when you shoot. This is a typical, or actually a photo from the first session. We did this at YLA, so this was the shooting for the music video. And as you can see, we actually had this. There was a kind of a paper. It's a huge QR code. At the time, we were experimenting with using a QR code to actually see where the floor was. So it's important, obviously, to know at what height your floor is. We've since moved on to do some other things, but at the time we were doing this. So as you can see, there are basically 3 Kinects set up in a kind of triangle space. The capture itself that we are doing is we have a custom RGBD file format. We put everything in there. We have a capability to compress as necessary uncompressed files at this resolution of depth. So basically, the thing about depth is that it's extremely difficult to compress. If you have a depth map, you cannot use conventional depth like compression algorithms. You can't really use JPEG or whatever on it because that totally messes up the depth information. So you have to do it either uncompressed or you have to do a special compression on it to get any kind of useful data out of it. So we've kind of worked on this quite a lot in the past year or so. The capture nodes are armed and then they're triggered from a controlling computer. Now for these captures we focused on just using 3 sensors. We have the capability, because of this system, we are not totally limited to that. We could have as many as we could, but as I said, you get interference, plus it's actually the more data you have, it's not necessarily any better. It depends a lot on what you're trying to achieve. Obviously, the more data you have, the more problems you're also going to get. So you might get artifacts, fireflies and so forth. And basically, prior to and during the shoot, if anything moves, we do calibration and then we do background filter frames. So first, for the calibration, it's important that we basically have something always on the floor. We use so that we can detect the floor. At that point, when we were shooting the YLA thing, we were using a QR code. Now we're using just objects on the floor, and then we also place objects high up, so that we can then basically later, when we're trying to find the different angles for the cameras in our 3D space, we have a lot of surfaces that all of the cameras see. This is important. And also we run background filter frames, so after we've done the calibration frames, we remove everything and then we shoot background filter frames that then we are able to then deduct from the actual data. So then we get an idea, or we can remove the background, so we get everything that we don't need automatically out of the image. Now, then moving on to post, after we've done the capture, we move on to post, because like I said, we don't have any clock between the cameras, and because there's an occasional drop frame, we're going to have to do manual synchronization between the actual captures. And again here, if we had, for example, 10 cameras running, and obviously we would have a lot more work to do. Now we only have 3, and we can synchronize them quite quickly by just adding a few keyframes here and there. The calibration actually is already we've managed to get to a position where it's actually pretty automatic. But it still requires a little bit of human eye to see that everything is good. And captured background frames set a threshold. Like I said, we do those background captures, so then we are able to deduct the background that is not needed in the scene. And we also take some fireflies out of the image. So the Kinect, sometimes you see this, they can be either dust particles or they can be some kind of tricks of the light. And you get them just for one frame, and there's a pixel somewhere flying. You want to get that out of the image, obviously. So we apply filters to do so. And then we also we have developed a few tools to clean away, just manually mask away unwanted elements from each camera's perspective. So, for example, if I was doing a capture here, and I just wanted to capture myself, and we wanted to remove the table, it would be we would just mask the table out of the depth frames. And then we move on to the Unity scene. So finally, when we cleaned up all the data, we create new RGBD files, and all the calibration and sync metadata is stored beside them. And now we can kind of import this data into Unity for playback. It could be any game engine, obviously. We focused on Unity because it has a very nice support for multiple different medias for playback. So we can show it on Android and so forth. Then we basically do shaders and geometry, and they determine the final look of playback. How does it look? And then we can also use creatively, because you have all this depth data. Then for example, you saw the little clip with the acrobats moving around in the scene. The lightning that was kind of coming out and that they were kind of hanging on to was actually just we calculated. We used the kind of the highest points of each frame, and then we produced lightning on those parts of the image. So you can kind of do tricks about if you want to do some creative work also using this unique data. The Unity pipeline is in more details like this. We basically create a static geometry for each camera, and it's exactly the resolution of the stored data. So for the Kinect, it's I really can't remember now the full resolution, but it's something like 520 times 400 per camera of depth pixels. And then we calculate, we have the static geometry, which we then distort. Or actually, we first compute the field of view and optionally also the lens distortion. This can be calibrated. We actually found this is something that might be of interest to you if you're planning to do anything similar. Each Kinect for Xbox, each of these devices, they have some variance between them. So it's a good idea to actually calibrate per device if you want the optimal quality, and you want for all the parts of the image to fit really well into the 3D scene. Anyway, we then take that geometry and we basically take the depth information coming from our file, and then we distort the geometry through shaders for each plane. So each camera has a single plane that gets distorted. So in essence, you could think of this. It's actually fake volumetric data in a way, because the cameras obviously don't know anything about each other. So it's in this type of in our solution, it's extremely important that the calibration is done perfectly, because we don't really take any kind of later modifications into the we don't compute any later modifications so we don't and this produces an effect which is also why I wanted to kind of pinpoint the importance of having some kind of a decided perspective, initial perspective for the user, because now as you kind of start to move from the initial perspective, you start to move from if I was the camera, and I would later then start to move towards another camera, which was another capture camera. Now, at some point, there's going to be some stitch, or there's going to be actually appearing a line, a kind of a stitch between the different parts of the, because these are two different meshes that I'm actually looking at. So there's bound to be some kind of a stitch between these, or a kind of a line running between these cameras. So you kind of want to do a perfect calibration, and then you might want to, as I'm going to kind of talk in a few minutes about, you might want to kind of try to hide that fact. But remeshing this data, so actually taking all the point information would be a totally different solution. So that would require, like I showed, it would require, first of all, a much better point cloud, so much better starting position. It would require, in order to create that mesh, you would require much better phase synchronization. So now, as I explained to you before, the phase between these cameras is not the same. So how are you going to mesh your data if one camera captures this frame and another one captures this frame, if the hand is moving like this? So we're kind of cheating in a way. We're trying to make things look as good as they can using this technology. Anyway, for then we take the geometry, we deform it based on the RGB the depth information, and we try to keep as many things on the GPU as we can. Obviously, it's quite expensive. At the kind of the amount of words that's happening, if you take these three cameras, we computed it's about 650,000 words. If you're trying to, if all of them were showing at the same time. But we are also discarding any unused pixels in the static geometry. So if we don't use them, we try to discard them as early as we can in the pipeline in order to create some headspace. So basically, that was the workflow recap. So that was the workflow, and the recap is that we have hardware. We have the hardware setup phase. In this case, very simple: 3 Kinects, 3 PCs, and a controlling PC. We then capture the scene and capture the calibration and the background frames. Then we do post for it. We calibrate, sync, and clean up the data. Finally, re-render the files in order to also save space. So this data still takes a lot of space. If you come check it out, the other project is about 3 gigabytes at the moment. There's maybe 10 minutes, 15 minutes of show. And then we import it to Unity. We create the scene, do a lot of shader stuff, and then try to make it look as good as it can in terms of that. But then, because we're kind of stuck to using this type of to use a limited hardware because of our budgets, and also because we want to be creative, then you can kind of take steps to make it more fun for you. But it's also important to just understand where this type of technology fits in this whole ecosystem, or where I believe it fits. Now, I think that taking kind of the bigger picture, looking at the bigger picture, one of the biggest issues for VR is that might be a technology that might be difficult to understand unless you get to try it out and you kind of understand where you could use it in your corporation or governmental organization. But most of these companies are very fond of video. They've done video and audio for years. Now this is and I kind of I thought about a little bit about this, and I feel that this particular type of capture it could also relate to. I haven't really thought about, I was talking about the so-called inside-out capture I call it inside-out, where the type that Facebook does. For example, Facebook was presenting this great volumetric video capture system, which was basically a 360 capture system where you can move your head after the capture. No, that's another. I think it might also apply there. But basically, I feel that volumetric capture is somewhere in between video and motion and performance capture. So it's not either. You can't really think of it as something that's similar to either of these. But it's also, especially when you're working with something like off-the-shelf hardware like ours, you know, where we have the costs are running maybe for the hardware starting from €5,000, maybe compared to, you know, I don't know if you take the Microsoft approach, you know, you have a €500,000 studio built for it, but you can get away with a lot less budget. No, in terms of the production value, of course, this is very. It's a nice fit. I think it's a nice way to create a lot of content for VR, and this is where I think that it fits in the production value chain. It's somewhere between video. It's a little bit more expensive maybe, but it's also a lot more interesting, perhaps. But it's definitely not as expensive as motion capture. Not even talking about animation, which is super expensive. If you take Pixar, I don't know, a good animator does maybe 2 seconds of really great level animation a day. But from another kind of taking another aspect on it, it's also very interesting from the acting and directing point of view. So from it's very much like video because it's totally merciless. You know, if you capture a bad actor, you're not going to do anything with that. You can't really do anything about it afterwards, and you have very few tools to actually do anything interesting with the data afterwards. So it's better to take everything in one go at the moment. But it's also important for you as a director to understand that the people that are actually playing this content back are likely to move also. They're totally free to move, and that's the whole point, isn't it? So then it also presents a challenge for the director to understand and make use of this of this possibility. And it's also, like I said, it's also vital to make kind of to choose where the scene starts from. So are you going to use it as a kind of a possibility to produce people that are standing maybe 5 meters away, where the actual effect of the depth isn't that high? You might as well almost be watching stereo video, but if you move, or are you going to just place like we do in the circus scene, we kind of put you right into the action, where it becomes really interesting because suddenly you have this performance walking all around you, and you kind of feel we're very part of the whole scene. So just to kind of point out another part of the creative process. But then getting back to the actual point that I kind of feel is maybe the most important one, is that because we're kind of limited on our budget, and probably most of you are also, if you're working on VR, there's not, at least for creative purposes, there's not so much money. There's a lot of money probably if you're very kind of deep tech, but if you're more interested in the creative aspects, you might be running a little short, so you might want to use something like the Kinect or something that's coming out soon, something else. But in any way, you might want to be creative, and this is a perfect medium for that, because nobody knows what to really expect. This is a first for people when you see those performers right in front of you. It's the first time that most people are going to experience that, so you might as well use that to your advantage. So there, for example, just to kind of point out, for example, for the music video, we decided to run with the kind of very abstract graphics, whereas in the circus thingy, we decided to go for more realism. So it's your choice. But finally, I think that it's an interesting mix of this type of capture, like taking this captured characters and then placing them into your game scene or whatever. It's an interesting way of telling a story. Also, and it gives you some new chances to convey your message. So you have to just make do and be creative in that. Hopefully I'm running a schedule. Is it okay still? It's yeah. So summarizing, it's kind of, I wanted to, these are the 4 points that I wanted to stress. It's totally possible to build your own capture rig. We did it. Low battery, that's not, that's better that it comes now. Anyway, it's totally possible to build your own capture rig from off-the-shelf hardware, and you might as well start experimenting with it today. You don't need to wait for Facebook to release anything or whatever. But even on these limited capture setups, it's the most maybe the most interesting part of this type of capture. This is something actually that I omitted from my previous points, was that because you're reproducing human motion. Human motion is something that even if you have the best performance capture rig out there, you know, if you go to Audio Motion in the UK, you pay them a lot of money for a day of their motion capture facilities, and you clean up all the data and you have this fantastic motion capture data. It's not going to be the same as capturing something with the Kinect. This is funny, you're going to have something different. With this capture technology, you're capturing everything. So you're capturing the clothes, you know, if it's an animal that you're showing it, you know, you're going to get all those details of that person or that animal, you know, how the dancer puts their little finger, you know, somewhere. You might capture that, and that's something that makes this very different from I think from motion capture. So it's slightly different, and it has a very human feel to it when you see it in VR. So it's an interesting fact. It's also fabulous storytelling technology. But it fits some types of content better than others. So you know, obviously, maybe music videos, you know, educational content, maybe even adventure games. You know, if you remember those 90s, the golden 90s, you know, you would play adventure games where some of the characters were digitized. You know, I feel that this is a little bit of the same. You have the same types of limitations with this type of thing, but it's also a possibility. And finally, I think that it fills an existing market gap. So how do we do semi-convincing, you know, humans in a VR production without breaking a budget, you know? So I think that this is basically the 4 key points here. For us, next up, we're trying to use, or we actually managed to already do a rig where we have a DSLR attached. This is nice for the fact that we get a much better looking, better RGB texture to the capture, and it also takes away the problem of having the low light conditions for the Kinect, the 15 frames per second limitation. We're trying to further automate the workflow, better cleanup tools. We've done some experimentation for streaming. This is interesting. We can, when you're able to stream, then you're able to do mobile. And then finally, you know, obviously, should I win the lottery, you know, I would like to do some more expensive, higher quality capture setups because I think that it's an interesting place to be. So yeah, anyway, just before, maybe I get a few questions, hopefully, but if you would like to wait and you don't want to do any questions, you'll find me at the Finnish VR Association booth, giving the demos for a few hours after this presentation. So if you want to just see how it actually looks and want to talk, come there. Maybe somebody has a question. It would be great.
Yeah, let's hope it doesn't do that again.
Yeah.
You said that there was some sort of synchronization issue, that when you move in your hand, that one camera captures like hand like this, and then the next thing is like that. Then the other one does it like slightly further along in motion. Is it the synchronization point that one of the cameras starts later than the other, or is it there? some sort of like different delta between frames.
Yeah, it's just the fact that they're running, so they're all running basically 30 frames per second. It's locked, but unfortunately we don't know how the phase works in these devices. So we've tried to figure it out. It's just that they capture the frame, they start and capture the frame slightly different time. So the first option. So they're all capturing the frames are they're maybe off. What's the maximum? I mean, you can compute. I can't now remember. It's there's all maybe the chance of the difference is maybe was it 16 milliseconds or something between the maximum difference between the capture of these two differences because we are running 30 frames per second.
Yeah, so it's still running at the same sort of exact moment then basically, right? So they're just that you have to sort of sync some sort of skew the time.
It's just the moment of the actual when they take the frame. So the camera 1 takes it at 0 milliseconds, and camera 2 takes it at 15 milliseconds.
So it's a rather simple thing to compensate for.
Yes and no, but because you can't really generate any data, you know, you can't really interpolate the data. Then it's not.
No, I mean just shift.
Shift if you were able to. If you could compensate. If you could compensate, you know, if you were to figure out how to, for example, reset the cameras so that they would run at the exact same, because the clock seems to be very stable. If we could figure that out, then we would be able to have them take the exact same picture at the exact same time. But because we can, hopefully we're talking about the same thing.
I think there may be something. Okay, yeah, thanks.
Yeah.
So how did you solve this issue? Did you use some sort of like motion prediction or estimation?
No, it's just we don't do that. We just I mean it's an issue, but it's there. But fortunately, this is a thing that we learned over the years working with the Kinect a lot. When there's a lot of data, you know, the human eye is very. Let's say that it forgives a lot. You know, when you have that human form there, even if there's a slight frame synchronization issue, if there's a slight issue with the data, then the human eye will compensate for it. So it's an issue if you want to mesh, if you want to create a perfect mesh out of it. You know, it becomes a huge issue. But if you're just using the actual point cloud to show, then it's not really such a big issue for. Surprisingly, it's not a big issue. But maybe you want to see it, come try it out, and then you actually see it for yourself. Might make sense.
So is it apparent in the circus performance example?
Yeah. There are definitely. I mean, and another issue is what I pointed out is that occasionally we get a few drop frames. So then we have to basically just compensate. Yeah.
So you said that you go for the DSLR setups for like low light performance, but there is also like 120 frames per second or even more. So is that something that you are looking for? Because then you basically would minimize those problems. It's only like with low frame rates.
But in this case we would probably just use the DSLRs for the texture. So then we would use the high frame rate in order to get the because we cannot input clock into either of these devices. So like a very expensive DSLR might have this option to put a clock in, but we can't put a clock into the Kinect anyway. So then we're going to probably have to run the DSLR at 120 frames per second. And then we're going to just look at which of the 30 frame sets best fits the need of the Kinect. You know, So we then, because otherwise we're going to face, if we were running let's say a 30 frames per second RGB, you know, then you would introduce another issue, maybe possibly a bigger issue into the fact where the texture for the RGB texture would be even more off than it is already in the Kinect. So we if we had a huge budget, you know, buy a lot more DSLRs and have a green screen studio. But at the moment, we would probably focus on just making the texture as good as we can for the depth information that we get from the Kinect.
Okay, thank you very much, Julius.
Thank you. Yeah. Thank you.